How many worlds support life in the Milky Way galaxy? We don't know the answer. We only know of one at the moment. Although I think most people would guess that surely there must be other places, even perhaps within our solar system, where life exists. But we don't know that at the moment. And so what ultimately we can say, I believe, is that we should behave as if we're the only civilization currently present in the Milky Way. That should be our approach to the way that we manage our civilization and our planet and the way that we plan our future, even though it might not be right, because we have no data, essentially. The power of the Fermi Paradox, ultimately, is not dogmatic, it's the opposite of being dogmatic. It's saying, given that we have not yet observed anyone, what might the reasons be? And that's an interesting exercise. But it's not to say there isn't anybody out there. It's to say there's an observation here that we don't see anyone at the moment. So why might that be? So you're right, it might be everyone hides, or it might be that given what we know about the history of life on Earth, it's just very rare that complex living things emerge. Maybe they're tiny, maybe they're so advanced that they're in the solar system and we don't recognize them. So you can argue about the Fermi Paradox, but broadly speaking, it's the observation that we've looked a bit, and all our observations in the history of astronomy, of all the observations we've made, we have never seen evidence of anyone else. And and it is a paradox because there's been so much time and so many planets, and it would seem as if somebody should have done something that we could see, and they haven't, as far as we can tell. There's the development of nuclear weapons, for example. So at some point, you will develop nuclear physics if you're going to be a spacefaring civilization. So you will develop the ability to destroy yourself, which is kind of, it's not long. You go back 100 years and we didn't have the capability to destroy ourselves. Now we could choose to destroy our civilization. So it may be that those challenges are very difficult to navigate. It may be just kind of one of those, not quite a law of nature, but a law of societies. There's a name for it, it's called the Great Filter. So one of the arguments, so what we're asking here is there a filter that, let's say the filter's in our past. So let's say that it's just the difficult thing is for life to go from single cell life to multicellular life. And that does look difficult, by the way, as far as we can tell on Earth. You have to accept it's possible, except that the zookeepers don't hide themselves from the animals. So you could say they're pretty good at it. We're getting better at observing the universe and looking for signals in the universe and so on. So they're doing a really good job if they're sort of tracking our detection capability and continually avoiding, so I don't know, it's possible. Civilizations, when they get technologically advanced, also get intellectually and morally advanced. And let's say that they choose, perhaps for good reason, let's say they choose to remain hidden because they don't want to draw attention to themselves. Let's say it's inevitable that if you think about it carefully and you think there are other advanced civilizations out there, then you choose to remain silent. You hide yourself as best you can. It's possible that that's the way that a civilization would think. Maybe that's the logical thing to do. I find it difficult to believe, given human history, that that's the way that intelligent civilizations behave. We certainly haven't made any attempt to remain hidden so far. We've broadcast radio signals out to the stars, the Arecibo message, for example, albeit weak ones. We've launched on our space probes, like Voyager, maps, pulsar maps in that case, which shows the location of our solar system should any other civilization find it. So at least at the moment, we haven't come to the view, which may be a wise view, but we haven't got there, that we should remain silent. Quite the opposite. We've tried at every opportunity to broadcast our existence. Maybe that's because Carl Sagan argued, I think, that a sufficiently advanced civilization, a civilization that can build interstellar spacecraft and communicate across interstellar distances, perhaps is wise enough to have overcome those primitive instincts, the instinct to cause trouble, to fight wars, to to colonize, to walk over other civilizations. Perhaps it's inevitable that with technological advance ultimately comes wisdom. But it's a hypothesis. Maybe it is. Maybe it's just anybody sufficiently clever to build an interstellar spaceship will be also sufficiently clever to hide it and not draw attention to themselves. Maybe it's immoral, maybe it's like Star Trek. Maybe it's the prime directive. Maybe it's morally certain that if you're sufficiently advanced, you decide to take the position that you will never introduce yourself or interfere with another civilization. Maybe that becomes a kind of law of nature for sufficiently intelligent beings. Maybe that's conceivable as well. Another explanation for the Fermi Paradox might be that civilizations live and die. They rise and then they fall. And because of the sheer timescales involved and the sheer size of the galaxy, no two civilizations ever overlap. I once had the great pleasure of meeting Frank Drake, the Drake equation, a legend, in his house. And he also grows orchids. And I arrived at his house just coincidentally on the day that this rare orchid flowers. And it flowers for, I think, 1 or 2 days and then goes away again for the year and then flowers again the next year for 1 or 2 days. And he used it as an analogy. He said, well, maybe civilizations are like that. So maybe civilizations are like rare orchids, and so they flower and die and flower and die. And just because of the sheer timescales involved, none of them ever overlap. And so there could be the wreckage, the ashes, the fossils of civilizations out there. But of course, we'd have no way of knowing until we explore the galaxy and maybe find the ruins of these other civilizations. Who knows? I mean, it's quite plausible if you think about it. Are we going to exist in 10,000 years' time? It's to a large extent in our hands. Maybe we're sufficiently stupid that we won't exist beyond the next century. There's an idea in this field, trying to explain the Fermi Paradox, called the Great Filter. Now, the Great Filter can lie in our future or our past. So let's think about what it would mean for a great filter to lie in our future. That would mean that civilizations do arise in the Milky Way galaxy and get to somewhere like the position that we're at now. So they develop rocketry, they develop nuclear power, nuclear weapons, for example, they industrialize, but then there's a filter in the future that stops them becoming true spacefaring civilizations. So stops them becoming multiplanetary species and stops them ultimately traveling between solar systems to begin to colonize a galaxy. So why might that be? Why might there be a filter waiting for us in our not too distant future that's going to stop us going onto Mars and stop us escaping our solar system?
No. For me, the Fermi Paradox drives us forward. Why haven't we heard from anybody? Because we're not listening hard enough. We're not being diligent enough. We're not thinking it through well enough. So we at the Planetary Society support the search for extraterrestrial intelligence, but the search for extraterrestrial intelligence in the optical bandwidths, in what you and I call visible light. And as you may know, NASA is doing these tests using laser communication. In other words, instead of sending radio signals with wavelengths the size of this room, and so information packets spread out over the size of this room, you'd use light waves where the information packets are just a few 100 billionths of a meter long. And so you can get a lot more, it's fiber optic. You get a lot more, the comparison of fiber optic with traditional copper wire. You get a lot more information, a lot more bandwidth. So who knows, maybe the aliens are sending us optical signals. We missed the point. Come on. One way to be sure you never hear from another civilization and realize or validate Fermi's paradox is to not listen. So this to me is an obligation of a civilization, of a civilized society, is to present or to allocate just a little of our intellect and treasure to the search for extraterrestrial life, because there's two questions that get every one of us. Where did we come from? Where did we come from? And that's, by the way, what the Rosetta mission is working on. It's going to a comet, which is part of the seems to be, and says certainly part of the primordial solar system. So by understanding that, we'll understand more about where we all came from. And the second question is, are we alone? Could we possibly be alone in the universe? And to answer those questions, you have to explore space.
Talk about the universe, but particularly the two great pillars of our understanding of the universe that we've built over the last century, and we're still building absolutely now. Two of those pillars that I hope you're going to contribute to building in the future. The two pillars, two things that maybe you don't learn about at school, but you'll certainly learn about at university. One pillar is called relativity, which is Einstein's great contribution to science, and the other one is something called quantum mechanics, which is a fascinating theory. It seems very strange. You may have heard of things like Schrodinger's cats, things can be in two places at once. But actually, quantum mechanics is our theory of everything that happens in the universe other than gravity. And today, the place where we explore that in detail is the Large Hadron Collider at CERN in Geneva, the place that I work when I'm not messing around on television. So I want to give you some idea of what we're doing now at the Large Hadron Collider and what we hope to discover within the next year or two. So absolutely current cutting-edge research. But the first thing I think to say about the ambition, because I said we want to understand the universe and our two great theories of it, is to look at the sheer size of the problem. And that's one of the things that I think captured my imagination first when I first began to get into science, when I was 5, 6, 7 years old. It was the sheer ambition of it. Because this is a picture of the universe. This is actually a picture of the night sky. If any of you are interested in astronomy, that thing up there is the constellation of Orion that you can always see in the winter sky. But I want to I want you to focus on a piece of sky that's somewhere around here. I'm going to zoom in on it now. It's a piece of sky that you would cover if you took a 5-pence piece and held it about 25 metres away. So imagine taking a 5-pence piece and putting it 25 metres away over a tiny piece of sky. Well, a few years ago now, the Hubble Space Telescope, which is in orbit around the Earth, turned its gaze to that tiny piece of sky, the 5-pence piece bit of sky, and took a picture. It opened its camera shutter for thousands and thousands and thousands of seconds and just gathered the light from that piece of sky. It was deliberately chosen because it's a dull, uninteresting piece of sky. Actually, from the surface of the Earth, you would see virtually nothing in it at all. But this is the picture that Hubble took. And you see that it's anything but empty. It's called the Hubble Deep Field image. It's one of the most important and fascinating images in the recent history of astronomy. It's not empty. It's got lots of structure, lots of points of light in. There are actually over 10,000 points of light or blobs in that image. And virtually every one of them, over 10,000 of them, are actually galaxies, distant galaxies. So they're not stars, they're galaxies. Now those galaxies on average have 100,000 million stars like our sun. The most distant object in that image, and I'm going to talk a bit about how we know these things in a moment, but the most distant object is 13.2 thousand million light years away. It was actually discovered in this image only a few months ago. Now, light travels at 300,000 kilometers per second, 186,000 miles a second. And at that speed, it's taken over 13 billion years to travel from the most distant object in that image to Earth, to the Hubble Space Telescope. Now, when you think that the Earth is only just under 5 billion years old, it means that most of the light from most of the galaxies in that image began its journey to Earth before there was an Earth. And for some of the most distant galaxies there, they were over halfway here when the solar system was just a cloud of gas and dust. It hadn't yet coalesced into the sun and the planets and moons of the solar system. So imagine what that looks like. That's a tiny, remember, 5-pence piece of sky 25 meters away. Imagine what that looks like when you extend it over the entire sky. Well, this is a beautiful map of the observable universe. Every dot on that map is a galaxy, with 100 billion stars like our sun in it, at least. You see that the structure in there, they're not randomly distributed. It's very interesting. I'm going to show right at the end of the talk that we think we're beginning to understand where that structure came from. Just to get some sense of scale, that little line up there, you might not even be able to see it at the back, but that's the 1 billion light year line. So light takes 1 billion years to travel from one end of that line to the other. This is the observable universe. And I'm going to show you, there's a ridiculous number that I have to show you. It's better to show it than say it. This is the number of stars that we think are in the we know from observation are in the observable universe at the moment. 30,000 million stars. Just like our sun, some bigger, some smaller. 350 billion large galaxies, 7,000 billion smaller dwarf galaxies. That's the observable bit of the universe. We have pretty strong evidence now the universe is significantly bigger than that, but we can just see this blob surrounding us, the blob from which light has had chance to travel during the history of the universe. So the universe is big, is what I wanted to say to you. I don't know if you know a comedian called Woody Allen. He once said that the universe is probably infinite, which is a bad thing if you're one of those people who can't remember where they put things.
In 1980, so in the live shows, I show images that Voyager 2 took of Neptune and Triton. That's 1989. So when Cosmos was written, we hadn't been to Neptune. So we hadn't visited all the planets in the solar system at that time. So things have changed. But for me, it's one of the first and one of the few science books that put science in context. So it's not only about astronomy, it's about civilization, it's about knowledge, it's about how we progress as a civilization. So that's the thing that really I took from that. You know, I grew up with Carl Sagan, and a lot of the way that I look at the world now was formed, I think, by Carl Sagan. But actually, the simple thing, the best way I think of thinking about Einstein's theory is that what is the time? The time you can think of as the distance over space-time, the distance over the map between two things that happen.
Yeah.
Well, if I say what's the distance between Bucharest and Copenhagen, you would rightly say, well, it depends on the route. Obviously, it depends which way you go. It's the same here in space-time, but the distance you travel over space-time is the time you experience along that route. So if we take different routes between two things that happen, as we did right there, then you will measure different times on your watch, because the time is measuring actually the distance that the watch travels over the map. That's it. That is it. Actually, that's the central idea in relativity. When you put it like that, the time on your watch is the distance your watch has traveled over space-time between things that happen. Then you realize, well, you can take different routes, and so you measure different times between things that happen. That's it. I mean, there isn't anything else to it, actually. So it's actually no more complicated than saying there are different routes between cities. There are different routes between events. It's not unnatural to worry about that, what it means to have an origin to the universe, because Einstein didn't like it, right? He was worried about it, although he accepted it ultimately because that's what the evidence tells you. Now, I should say, now that we still don't know what it means.
Enrico Fermi is one of the great physicists, legendary Italian physicist, who laid many of the foundations of modern 20th century physics, so-called Fermi-Dirac statistics and all sorts of things. If you do a degree in physics, then you will spend a lot of time revising equations and theories that Fermi did. One of the great legends. The Fermi Paradox is it's probably the thing he spent least time on, actually. It's almost one throwaway remark that he delivered. And the question is, where are they? By they, I mean aliens. The heart of the Fermi Paradox is this. We know that we live in a big old galaxy, in a big old universe. And let's, for the purposes of this discussion, confine ourselves to the Milky Way galaxy. The Milky Way galaxy, we now know, has something like 400 billion suns. And we now know that most of those suns have planetary systems around them. So trillions of planets. The galaxy's been around for pretty much the age of the universe, 10 billion years plus. And so there's a lot of real estate, and there's been plenty of time for civilizations to develop in the galaxy. The Fermi Paradox, at its heart, is the statement that, notwithstanding the fact that there have been billions of years on billions of worlds for civilizations to arise, we see no evidence of any of them in the galaxy at all. So the paradox is why? It's a paradox. And I think it's a very good question. It's an extremely good question. And there can be many answers. And the great fun, or the great, I would say the intellectual value of the Fermi Paradox. So if we accept that we haven't seen any, so let's accept that. Let's accept that there isn't a UFO sat in some warehouse in Roswell or something like that. Let's accept that we haven't seen any. Let's accept, well, we have to accept the picture that I've just given you about the Milky Way galaxy and its age, because that's a measurement, so we know that. The question is then, why? How do we resolve these apparent contradictions and paradoxes? So one answer to the Fermi Paradox, this is the idea that we don't seem to see anyone, is that no one ever evolved. Right? So life didn't get complex. Why might we think that? Well, what did we need to produce our civilization on this planet? Well, on this planet, one thing we needed was time. We have good evidence that life was present on this planet 3.8 billion years ago, perhaps even earlier. The planet is 4.5 billion years old. So we know, as a matter of fact, as an observation on this planet, that life was present 3.8 billion years ago. But it took 3.8 billion years, give or take a few tens of thousands of years, to go from the origin of life to a civilization. Let's say from cell to civilization. 4 billion years. That's 1/3 of the age of the universe. So a possible answer to the Fermi Paradox, the question of why there are no civilizations, is because the Earth is pretty much unique in the Milky Way galaxy, in that it was stable enough, the climate, the conditions on Earth were stable enough for long enough for life to go from cell to civilization. If you think about it, that's a big ask. What I'm saying is, on this planet, an unbroken chain of life existed for almost 4 billion years, notwithstanding the fact that we live in a violent universe. The sun must have been stable enough for long enough. We know the output of the sun has changed over those billions of years, but it's not changed so radically that it managed to erase, destroy life on Earth. We know that we live in a violent universe. We know there are supernova explosions all over the place. It turns out that there have been no stars massive enough to explode as a supernova in a way that would damage life on Earth or erase life on Earth in this vicinity for 4 billion years. We know that nothing has happened. We know that there have been impacts on the Earth, right? We know that the famous impact that wiped out the large dinosaurs. Maybe it's the case that whilst there are billions of planets which may have liquid water on the surface, may have oceans that can support life, it may be that none of those planets in the Milky Way galaxy have been stable enough for long enough to produce a civilization. So that would be a property of the planet itself, the so-called rare Earth hypothesis. Actually, I should say, it's a property of a solar system. It's not really just a property of the planet. It's a property of the parent star. You could ask the question, well, if it was a binary system, for example, a binary star system, many stars are binary star systems. Is it possible to have a planet with a stable climate, stable enough orbit in a binary star system to support an unbroken chain of life for 4 billion years? Perhaps not. When we talk about rare Earth, I think I would like to talk about rare solar system. Another possibility with the Fermi Paradox is that it's not a paradox, they are here. So there are intelligent civilizations out there and they are present in the solar system. It's possible. Let's think, for example, what such an intelligence might look like. Well, who knows? They could have sent nano machines to our solar system. There could be probes all over the place in the solar system, but if they're the size of an iPhone, then we'd have no way of detecting them. So it could be the technology of a sufficiently advanced alien species, a civilization, is so beyond anything we can comprehend or detect that we haven't seen it and we've been fooled into thinking that there are no advanced civilizations in the galaxy. And that's certainly entirely possible. Another possibility, another possible resolution to the Fermi paradox is just that the galaxy is so big. The distances between stars are so great that if you imagine there's another civilization, let's say on the other side of our galaxy, let's say 20 million, 30 million, 40 million light years away, even if they had the most powerful radio transmitters you could imagine, or even if they'd spread out to neighboring solar systems, then it may just be that the distances are so great that the signals are diluted, that we can't detect them because they're too weak, or that it's just very, very, very difficult in an engineering sense to build interstellar spacecraft. Now, perhaps you can build a spacecraft that can hop a few light years away to the nearby solar system, 4 light years in our case to Alpha Centauri, but you can't build spacecraft that can traverse a galaxy. That's a possibility. One of the arguments against that for me is the argument, it's called the space travel argument against the existence of extraterrestrial life. And it's often framed in terms of self-replicating machines, so-called von Neumann machines. So imagine it's possible for us, for a civilization, to build a machine, some kind of AI, that's sufficiently smart and capable that it can fly to a nearby solar system, reproduce itself, copy itself, and then send the copy out to the next solar system, and so on. So you have, if you build a one successful replicator, you have an exponentiation of replicators. You have 1, and then 2, and then 4, and then 8, and so on, exponential growth. And you can show that even given our rocketry technology, you can cover a galaxy like the Milky Way in a reasonably short space of time. By reasonably short, I might even mean 100 million years, right? That's reasonably short on galactic timescales. But the key point is once a single successful replicator has been launched, then it is inevitable that over a few tens of millions of years, the galaxy will be covered with replicators, and we don't see any evidence of them. It's possible that we can infer that if we assume that we could detect them, then the absence of them may allow us to infer that no civilization has ever got to that point. And I think that's quite a persuasive argument. Now, it's possible that there are many civilizations out there, but the advanced civilizations choose to remain hidden. Sometimes called the dark forest hypothesis, the quarantine hypothesis. If they exist, liquid water below the surface, who knows? I wouldn't be surprised if we find microbes all over the place. But a galaxy full of complex living things, other planets with not only complex life, but sentient life, things as smart as us, things smart enough to build rockets and head out to the stars. My guess is that a typical galaxy may have less than, on average, less than one civilization per galaxy. Let's put it that way. And actually, just to say, there's a very famous book I'd strongly recommend, Barrow and Tipler, called The Anthropic Cosmological Principle. It's a great book, one of the books I grew up with. And in that book, Barrow and Tipler say that in their view, there might be one civilization in the observable universe.
SETI, S-E-T-I, has always had an interesting relationship with the idea of transmission, of communication. In fact, when the field first began, it was actually called CETI, and that C stood for communication. And very quickly, they changed their minds and realized that the idea of a two-way communication was maybe a bit ambitious, and it might be better just to focus on searching for the signal rather than truly trying to have a dialogue. So on the other side, we have the idea of METI, messaging extraterrestrial intelligence, also called active SETI. So this is where we actually send out a message hoping to get a reply at some point in the distant future. Of course, that could be hundreds or even thousands of years, given the vast expanse of space beyond us. So this is a very common concern. Stephen Hawking had the concern that, maybe we should be very careful about communicating to the civilizations, because whenever you've had a more advanced civilization engage with a less advanced civilization on the Earth, that has usually ended very badly for the less advanced one. And so if you extend this out to the galaxy, maybe we should be careful about sending out our presence into deep space. And certainly this is a trope that has been played with in science fiction as well. If you look at Liu Cixin's book, The Three-Body Problem, that's where we get the idea of the dark forest hypothesis, the idea that civilizations could be out there, dangerous, marauding ones who want to take over and colonize your planet, and so it's much better to just be quiet. Don't let anybody know that you're here. I do have a bit of an issue with this idea of resistance to METI and resistance to communication, and that's that we, humanity, are already engaged in the activity of trying to build telescopes and future facilities that can detect life whether they want to be detected or not. So you don't have to send out a radio wave for me to be able to detect your civilization. We could potentially detect their satellite systems, their Starlinks. We could detect their solar panels on their surface. We could detect their industrial space presence, even the chemical pollutants in their atmosphere from industrial processes. There are so many ways that we could imagine being able to tell there was a planet that had a civilization on it, an advanced civilization on it, without the need for a radio message, that it's a little bit archaic to assume that that's the only way that a civilization would be able to know of another one's presence. I suspect if there is another advanced civilization out there in the galaxy, they already know that we are here. Maybe not the presence of Earth's current level of technology, because simply the finite travel time of light is, going to limit us to about 200-year radius, essentially 200 light-year radius, where another civilization would know that we're doing industry. But certainly beyond that, in the broader galaxy, they would know we had an oxygen-rich atmosphere, they would know we had photosynthesis, they would know that the Earth was inhabited by creatures. And so I think it would be difficult to argue that we should be very, very quiet, because otherwise they will never know we're here. I suspect they are well aware that this planet is inhabited with or without our radio signals.
For those of you who for some reason are not obsessed with the Fermi Paradox, Enrico Fermi posed the following, same guy with the nuclear reactor in Chicago and all that, posed the following question: if there are alien worlds, as you might claim, since there are billions of stars in billions of galaxies, you would expect billions of planets, and then you'd expect a few millions Earth-like planets. Why haven't we heard from these other civilizations? And the answer, I think, is not that complicated. We've only been listening for other civilizations for 50 years, 70 years, depends how you count. And you have to acknowledge that civilizations have to emerge and be able to communicate at the same time. When you have something that's been going on for 13.6 billion years, there's a lot of opportunities to miss each other. So the Fermi Paradox, for me, is not a reason to give up and take the black capsule and have no hope for humankind, because we are just this unique thing in the middle of nowhere. And
these are called von Neumann probes. Von Neumann probes are probes that make copies of themselves and shoot out to the next generation of planets. They then colonize those planets and shoot out once again. So with one probe, you have two. With two probes, you have 4, 8, 16, 32, 64, 128 probes, until you have a sphere of billions of probes expanding near the speed of light, or perhaps even superluminal velocities, colonizing the galaxy. That is the most mathematically efficient way to explore the universe. Forget the Enterprise in Star Trek. The Enterprise goes from hopping from planet to planet to planet. That is the most inefficient way to explore the galaxy. The most efficient way to explore the galaxy was von Neumann probes that land on moons, make copies of themselves, they shoot out. And where have you seen that before? That's a virus. That's exactly what viruses do. Viruses land on a cell, hijack the machinery, create copies of themselves that shoot out, they make more copies of themselves. That's the most mathematically efficient way to colonize the Milky Way galaxy. And that's what an advanced civilization would do, because you only have to make the first probe. Once you make the first probe, like a virus, it just self-replicates all by itself. Well, first of all, where do correct ideas come from? In part, correct ideas come from interactions with incorrect ideas and also experiment.
Why would we study these things? Well, in studying these things, we're beginning to get a deep picture of what our reality actually is. And that's a remarkable idea, but it's a beautiful idea that runs through all of. Well, it's in Einstein's theory, which again is a remarkable thing. It's published in 1915, over 100 years old. But it's just a region of space from which even light can't escape. Well, so Stephen Hawking, back in the 70s, published a paper. The initial one was called Black Hole Explosions, which is a great title for a paper. He calculated, he found out that black holes, in his language, he said black holes ain't so black. They glow in the sky, like coals in the sky, and they radiate. And so over time, they lose energy and mass and ultimately disappear over huge timescales. And that's so important. And I show this picture in the show, that if you go into Westminster Abbey and look on the floor of Westminster Abbey, on Stephen's memorial stone, then you find his equation for the temperature of a black hole literally chiseled in stone on the floor of an abbey. So you might say, why? Why is it so important? This was the key. This was this Rosetta Stone idea in trying to understand what happens. What happens to the stuff that fell in? It was when you thought these things existed forever, which is pre-Hawking. Then you think, well, it's okay, it gets locked up inside, it can never get out, we don't care. But the thing evaporates away, one day it will be gone. So then suddenly you have to be faced with this question, what happened to everything then? If I throw a book into a black hole, is it somehow possible in the far future, if you collect all this so-called Hawking radiation that comes off, is it possible to reconstruct the information in the book? And that's been a question, simple question, that's driven this tremendous amount of research for 50 years. And it was pretty much solved in 2019, actually, and 2020. Pretty much. I mean, there's still a huge number of questions, but roughly, the statement is everything comes out again, all the information comes out. So everything that fell in principle, in the far future, you could reconstruct the information of everything that fell in. It's an astonishing idea. Because the last thing I'll say is that before the Hawking papers and before this modern understanding, inside a black hole, just according to Einstein, sits the end of time, which is an astonishing thing to say, because we can see them. We have a photograph of one of these things in the center of a galaxy, two actually now. And when you look at that photograph, you're looking at the end of time in space. So then you think, well, if things go to the end of time, how does everything get out again? Yeah. And that's the content of this tremendous work in theoretical physics. This work, studying black holes, which is it's one of those things that a certain kind of person says is useless, right? You say, why? Who cares, right? It turns out that the techniques that are being developed and the understanding that's being gained from looking at these things has got a very strong crossover with building quantum computers. Right, which is quantum computers are in laboratories now. They have a tremendous potential to revolutionize our civilization. Incredibly powerful computing devices.
We're talking about out of 100 billion stars in the Milky Way galaxy, we're talking about billions of potential Earth-sized planets. And to believe that we're the only one is, I think, rather ridiculous, given the odds. And how many galaxies are there? Within sight of the Hubble Space Telescope, there are about 100 billion galaxies. So do the math. How many stars are there in the visible universe? 100 billion galaxies times 100 billion stars per galaxy. We're talking about a number beyond human imagination. And to believe that we're the only ones, I think, is rather ridiculous. Well, first of all, we have to understand the level of sophistication of an alien life form if we make contact with them. I think in this century, we'll probably pick up signals from an extraterrestrial civilization. We'll pick up their I Love Lucy and their Leave It to Beaver. Just ordinary day-to-day transmissions that they emit. And the first thing we want to do is to A, decipher their language, of course, but B, figure out at what level they are advanced on the Kardashev scale.
We are physically insignificant, but it is possible to argue that we are remarkably valuable, notwithstanding our physical insignificance, because it's possible to at least argue that the number of civilizations in a galaxy like the Milky Way might be on average 1 or less, is essentially the question, where are they? You base that on the observation that, let's say there are somewhere between 200 and 400 billion suns in the Milky Way, something like that. We think a lot of them have planets. Many of them have potentially Earth-like planets. So you have 13 billion years of time. You have hundreds of billions of suns, probably trillions of planets. And so it is a reasonable question to ask, why not? Why has a civilization not arisen ahead of us? So let's say 1 billion years before us. Why has no civilization escaped its home world, apparently, and essentially written its existence across the sky? Why is that? Why don't we see anybody? One of the arguments is often framed in terms of self-replicating machines, so-called von Neumann machines, after the great mathematician John von Neumann. And so essentially the idea is that what are we? What's a human being? It's a replicator, right? So it's a physical object. It operates according to laws of physics. That's what we do, and we replicate. And so it seems that there's no reason why we couldn't build replicators that are essentially, AIs basically, right? It's almost like an AI-controlled 3D printer with some mining stuff attached to it, and you send it off to the asteroids or to Mars or to Alpha Centauri, to the system there and all the raw materials will be there to allow this thing to replicate. And then you can build a kind of a model of that, how those replicators might spread throughout a galaxy. And people have done this, of course. There's a great book, as an aside, I would recommend, by John Barrow and Frank Tipler, which is a huge influence on me, called The Anthropic Cosmological Principle. And it's a very famous book. There's a great series of calculations in there just showing you how you might estimate, if you could build one of these self-replicating machines, how long would it take, given some reasonable technology, to move between star systems? How long might it take to replicate itself? And you end up with calculations that say that if someone had done that, even a few 100 million years ago, those machines would be everywhere. It's like a virus, right? In a sense, it just propagates. It's an exponential growth of these things. And so you would cover the galaxy in them. And it is true that we haven't observed any. So you might say that that's evidence that nobody ever did it.